Hi, this is Lance Bradfield, and I'm going to be recording a extra credit opportunity for chemistry, and I am choosing to do the 11th chapter, end of chapter questions, and so we'll go and get started with number 48 here. So, the density of a 9.61 molar H2SO4 solution is 1.520 grams per centimeter cubed. Calculate the mole fraction of H2SO4 in this solution. So, let's just start off with what the mole fraction is. Well, the mole fraction, or x, is equal to the moles of a component over the moles total, or n. So it can be n. In this case, it's going to be n of H2SO4 over n total. So this is what we want. But let's not get ahead of ourselves here. And so let's find, or let's just think about what molarity is. Let's think about what this number right here is. 9.61 molar. Well, what is molarity equal to? Well, we know that molarity is equal to moles over liters, right? So if we have, so let's try and think, what would be an ideal liter amount to have for us to get in a nice mole, just a nice amount of moles? In this case, it would probably be 1 liter, since we can just get the 9.61 moles in that. And so let's think, so just to make sure, that's moles per liter. And so that's moles per liter. So that's all good. So from here, we know that we now have 9.61 moles of H2SO4. So let's see, what else can we do here? We know that the entire solution has a weight of 1.52 grams per centimeter cubed. Well, let's see, where can we apply that? Well, we know that we're going to use a liter, and so 1 liter is equal to 1,000 milliliters, and 1,000 milliliters is also equal to 1,000 centimeters cubed. Well, if we have the amount that we know and also how much it weighs, well, then we can just multiply by 1.520 grams per centimeter cubed, right? And so whenever we're multiplying this, these two will cancel out, so that all that we're left with is 1,520 grams of solution. Sorry. So this is the entire weight of the solution. But in order to get the amount, or in order to get the mole ratio, or mole fraction, we need the moles. So we have this, which this is going to end up being our numerator, but we don't have the n total. Well, what else are we missing? Well, if it's a solution, we can figure that it's probably going to have water as the solvent. So let's see, what can we do here? Well, we can take this H2SO4 and find its molecular weight. And so the molecular weight of H2SO4 is equal to 98.08 grams per mole. Well, how many moles do we have? Well, we've already found that. It's right here. So this times 9.61 grams, or moles, sorry. Well, moles will cancel out, and so we are left with 942.5488 moles, or grams. Gosh darn it. So now that we know that, we can take this away from the total. So now we can take this away, and 942.5488 grams, just grams right here. And so we will be left with 577.4512 grams. Well, what is this? Well, it's our only leftover component, and that would be water. So we know that the molecular weight of H2O is equal to 18.0152 grams per mole. Well, this time we're not going to be multiplying anything. We want how many moles of water we have. So we can take this 577 of H2O and turn this into moles by dividing. So 577.4512 divided by 18.0152 grams per mole, and this is grams, so that cancels out. So what are we left over with? Well, we have 32.05 ... moles. So now we have the moles of the entire solution, so we can just add those up. So we're going back up here and going to use this. So we already have the moles of H2SO4, and we know that to be 9.61 moles of H2SO4. And this is over the 9.61 moles of H2SO4. That plus 32.05 ... moles of H2O. And so we are left with a mole fraction of H2SO4 equal to 0.231. So that's our final answer. Moving on to number 72. The normal boiling point of methanol is 64.7 degrees Celsius. A solution containing a non-volatile solute in methanol is prepared. If the mole fraction of solute in the solution is 0.268, determine the vapor pressure of the solution at 64.7 degrees Celsius. So let's think. What do we have here? So we know that the mole fraction for the solute is equal to 0.268. So from here, we can actually find the mole fraction of methanol in this same solution, because whenever we have a mole fraction, it always has to add up to 1. So if this has to add up to 1, then we can take this X of the solute plus the X of the methanol and add it up to get 1. So instead we'll just subtract this X of solute, which we already know is right here, and we'll get X of methanol, or the mole fraction of methanol, to be 0.732. So from here, we can actually just go straight into the equation that we need to use. And so we can just use the P of the solution is equal to the X of the solvent, P solvent, plus X solute, times the P solute. So there's also one more thing that we need to understand here. So we know that the solution is containing a non-volatile solute. So that means that it won't contribute to the overall vapor pressure. So we don't even need to use this. So this is essentially, this right here is 0. So we can just use this new P solution equals the X of, in this case, methanol, times the P of the solvent. So let's see. So let's just go ahead and plug and chug right here. So the P of the solution is equal to the 0.732 times the, sorry about that. I got a little caught up on my words. So this is actually correct. So it's 0.732. And then we are going to be multiplying by the pressure at which this is true, and that would be at 1 atmosphere. So in this case, the pressure of the solution is just equal to 0.732. So it makes sense that it wouldn't be the normal, right? Because if we were going to have a 1, it wouldn't make sense here. It would make sense that it is going to be less than, because we have a non-volatile solute in the entire solution. So if we think about the top of the beaker and we have the methanol and solute in here, we can, or this is actually going to be pure methanol. This is going to be pure methanol. And so I'm just going to color this entire thing in white. And so if we imagine it like this, then we can see that there's vapor coming up all over the place. It's at least all going to come out, right? But if we have a non-volatile solute in there, and it's at 0.268, so it's going to be a little over a quarter. So I'll just draw a quarter right there. So that means that only this much is actually going to be able to evaporate off the top. And so we only have that much, right? So it's really only going to be about 3 compared to that 5 over there. So it makes sense. It does make sense for the question that it would be less than 1. So this is our answer right here. So now number 73. At 40 degrees Celsius, heptane has a vapor pressure of 92 torr and octane has a vapor pressure of 31.2 torr. Assuming non-ideal behavior, what is the vapor pressure of a solution that contains twice as many moles of heptane as compared to the moles of octane present? So let's think about this. We have a solution, and we're assuming that it has ideal behavior, just like in the last one. I forgot to mention that, but we were assuming ideal behavior in the last one as well. What is the vapor pressure of a solution that contains twice as many moles of heptane, so up here, as compared to moles of octane? Octane, which is right here. Well, let's see. So if we have a solution, and let's say that, again, we're going to have our entire mole fraction in this solution is going to have to equal to 1. Well, how are we going to get it to equal to 1 if we have 2 parts to 1 part? Well, let's see. So if we multiply this by 2, and then another 1 by 1, then we get 2 and 1. So if we add these together now, we get 3. So if we divide each of these by 3, so we'll have 2/3 of the solution that is heptane, and we'll have 1/3 of the solution, which is octane, then we can use these as our mole fractions right here. These are good enough to use. So we can just go ahead and set up the ideal equation again. And so we can have X of methanol times the pressure of methanol at 40 degrees plus the mole fraction of octane at 40 degrees, or that is not dependent on the 40 degrees, sorry, times the pressure of octane at 40 degrees. We can just go ahead and plug this in. We already know that this is going to be our methanol, that this is going to be right here. And so now we can just see from we already know the pressures from up here, and that's the 31.2 and 92 torr respectively. So let's go ahead and plug those in. So the pressure of the solution is equal to the X of the methanol, which we found to be 2/3, times the pressure of the methanol at 40 degrees, which is 92.0 torr, plus the 1/3, which is from right here, times the pressure, which is 31.2 torr. Well, then we're going to end up getting a vapor pressure equal to 71.7 torr. Because we're just going to bring these down right here. So that makes sense, right? Because I mean, if we have 2/3 of something that is that has a much higher value in the pressure slot, it's going to be closer to 92, which it is. It makes sense. And we only have 1/3 that's closer to 31.2. So this answer does make logical sense. So continuing on to the last one, number 127. A solution is made by mixing 50 grams of acetone and 50 grams of methanol, CH3OH. What is the vapor pressure of the solution at 25 degrees Celsius? What is the composition of the vapor pressure as a mole fraction? Assume ideal solution and gas behavior. At 25 degrees Celsius, the vapor pressures of pure acetone and pure methanol are 271 and 143 torr, respectively. The actual vapor pressure of the solution is 161 torr. Explain any discrepancies. Okay, so let's just continue on from here. And let me just flip over my notes real quick. So we already know from previous problems that we're probably going to want to set up the ideal solution equation again. So it's just this and then acetone, pressure of acetone, plus the X of methanol, or mole fraction of methanol, sorry about that, methanol, times the pressure of methanol. So let's see, what are we given in the question? Well, we are already given the pressure right here and right here. And so we can continue on from there. Sorry, I got distracted. Somebody walked into my room, but no worries. So let's see. We need to find the mole fraction because we're already given the pressures and we're trying to find the pressure of the solution. Then let's see. What can we do from here? Well, we know that we have 50 grams of acetone. We have 50 grams of both. So let's assume that we're just going to combine both of them and let's see and that's it. We aren't going to add any water. We aren't going to dissolve it in anything. We aren't going to we're going to treat them both as one as a solvent and one as a solute. So how many grams per mole is acetone? Or let's get a mole fraction for both. So we know that a mole fraction, so in this case for acetone would be equal to the moles of acetone over the molar total. Well, we don't know this and we don't know this, but we can find both of them actually. So if we know the molecular weight of acetone, which is equal to 58.08 grams per mole, and we know the molecular weight of methanol, which is 32.04 grams per mole. Then we can just continue on from here with the fact that we know that we have 50 grams of both. So if we divide 50 grams, 50.0 grams of acetone by 58.08 grams per mole, then these cancel out and we are left with 0.86088 moles of acetone. And over here, if we take the 50 grams and we divide it by 32.04 grams per mole, then we can go ahead and find how many grams of methanol we have as well. And we have 1.561 ... moles of methanol. Well, if we add these together, we'll get the molar total. So let's go ahead and find that. The molar total is equal to about 2.42143 ... So we actually have all of the values that we need to plug into this equation. So X of the acetone is equal to the acetone, which is right here, the moles of the acetone, which is 0.86088 moles over the total moles, which is right here. So we'll go ahead and plug this in. 2.42143 ... total, or not total, but just moles. So these cancel out, and so we're left with a unitless number, just like in the last questions, of 0.3555. So instead of going through the entire thing of setting this up again, we can just actually subtract, like in the last ones, from 1, because x plus x, or mole fraction plus mole fraction equals 1. Our mole fraction here is this, so x of methanol, or the mole fraction of methanol, is just going to be equal to 0.6447. So let's go ahead and plug these both into our original equation up here. So the pressure of the solution is equal to 0.6447 times the torr. This is methanol, so we're going to plug in methanol, which is 271 torr, plus the 0.3555 times 143 torr, and we will get AP, or a pressure of the solution, that is equal to 189 torr. But that isn't it for this question, so let me go ahead and get another page. So now we want the vapor pressure for the, or we want how much, or we want the mole fraction of each of the for the solute and solvent in the vapor. We want the mole fraction of them in there. So for the vapor, I'm just going to put for the vapor so we know what we're doing. So the mole fraction for the vapor of methanol is equal to the X of the methanol, or the mole fraction of the methanol times the pressure of the methanol over the total pressure, which we have all of those. So let's just go ahead and start plugging in values. So that's going to be the same value that was up here, right here. So I'll just go ahead and put that in, and that's going to be 96.3405 torr over 189 torr. And so that's going to leave us with a value of about 0.511, and that's for the mole fraction. Let's move that over a little bit. For the mole fraction of methanol, 0.511. So in order to find the mole fraction for acetone, we can actually just do what we did up here again, up here, right here. And we will just subtract this from 1. So we will just do mole fraction plus mole fraction equals 1. we already know this. We'll just say we know this one. So this is going to have to be equal to 0.489. So this is an answer. This is an answer. And this is an answer right here. And so looking at the question, we know that the actual vapor pressure is supposed to be 161. So we are higher than the actual if we look right here. So the original vapor pressure is less than the new, therefore indicating a negative deviation from the ideal Raoult's law. This negative deviation means a lower vapor pressure, indicating stronger attraction between the unalike molecules. So we have a stronger connection between methanol and acetone than we do with methanol, and acetone. It is more, this is more like the actual. So it creates it makes it harder to escape, therefore increasing the vapor pressure and making the torr higher than it really is. So that's it. Thank you.